Another type of question which is asked related to the design of compression member is this type of question. That is, here an ISSP section having a particular length will be given and based on a particular support condition, and we have to determine the design axial load, which is PD. Now in this question, an ISHB, HB means heavy beam 300 at 576 Newton meter is used as a column which is 3 meter long with both end restrained against rotation and translation. So this is a support condition and we have to determine the design axial load. And design axial load is a load which is given in clause 7.1.2, that is PD value, which is in page 34. Now what has the given data? We are given the length 3 meter, so which means 3000 millimeter. So now what will be the effective length? So here the restraint conditions are given as it is restrained against rotation and also against translation, which means it is a fixed kind of a support. Now if you go to table 11 of page 45, you go down, we can see the condition against restrained against rotation translation, and the value will be 0.65, the value of k. So the effective length KL will be 0.65 times 3000, which is 1950 mm. Now we have to go to IS 808 and we have to check the various data related to this standard section. Now 576 Newton meter ISHB 300 is almost equal to 70. It's basically its mass will be 58.8 when we convert the Newton in kilogram. So we have to consider that ISHB 30. So don't take the below one. So we have to take this ISHB 80. Now the sectional area given is 74.8 centimeter square, which is the effective area. So this in millimeter, this will be 7480 millimeter square. And for our design of compression members, the slenderness ratio, the least radius of gyration is an important factor. So here the Rx and Ry, X and Y basically denotes two axes. The minimum radius of gyration will be along Ry, which value is 5.41 centimeter. So we will be writing all this. So the sectional area will be 74.8, which is 7480 millimeter square, and the Rx. So this details of this designation are given in IS 808 steel table page number 5, and the Rx is 13 centimeter, which is 130 mm, and Ry is 5.41 centimeter, which is 54.1 mm. And the height is basically D means the height of the uh, ISMB section, which is 300. B is the width of the flange, which is 250, and TF is the thickness of the flange, which is 10.6. So all these things has to be noted because we have to select the class. So the important thing is we have to find the slenderness ratio, we have to select which buckling class, and then only we can design the compressive strength, which is FCD. Now the next step after writing all these parameters from page number 5 of IS 808 or the steel table, we have to select the buckling class for this ISMB section. So for that we have to go to table 10, which is in page number 44 of our IS 800. Now we see so many sections, I sections, channel sections and all. Now we have to select the ratio of H by BF. So H is the height, so there is a figure given in the I section in the left side. H denotes the height, which is 300, and BF means it's the width of the flange, which is the B value which we written earlier, which is 250. Now the ratio of H by BF, when we calculate 300 divided by 250, gives 1.2 value. Now this is less than or equal to 1.2. Now what about the thickness of the flange, which is 10.6, so this is less than 100. So we have to select the second row where there are two axes given of the condition for H by BF less than or equal to 1.2 and TF less than 100, and for ZZ axis, which it will be in buckling class B, for YY axis it will be in buckling class C. So there will be a strong axis and a weak axis is there. Now always the critical buckling will be in the axis where the radius of gyration is minimum. So we know that the radius of gyration is minimum on Ry. It is obtained from the sectional properties of the member from IS 808 itself. So the Ry was 5.41 centimeter, whereas Rx, which is equivalent to our RZ here, was 13 centimeter. So the minimum value was obtained in y-axis. So that axis will be more critical towards buckling. So we will be selecting that axis, that is buckling we assume to be more critical in YY axis, and the buckling class related to that axis obtained from table 10, which is in the second row, will be C class. So that's why we are selecting this class. It's a very important step in the design of compression members. And we can calculate the design compressive stress FCD. Once we calculate the FCD, that multiplied by the sectional area of the ISMB HB 350, you will be getting the total design load. Now our IS code has three methods. Basically, there are total three methods to calculate this design compressive strength. And the first method, so we can do any three methods, and always the last method is more accurate and it's more like reliable. So other two methods are based on tables, so it gives a quick methods. So in first method we will be using stress reduction factor, that is table 8. There is table 8a, 8b, 8c and 8d, and a, b, c, d is for each buckling classes. So we know that in clause 7.1.2 in page 34, FCD will be equal to this stress reduction factor psi multiplied by Fi divided by gamma m0. So there is another equation near to the original equation which we discussed earlier, phi and lambda. So there is another equation. So we can also use that to find FCD value. Now, how can we find the stress reduction factor? Now, stress reduction factor can be calculated based on the slenderness ratio. So that is when we look at table 8A, because it is C class, we have to refer table 8C of page number 38, and we have there we can find the value of the stress reduction factor based on the yield stress and slenderness ratio. Now we have to calculate the slenderness ratio for this particular question. So slenderness ratio basically is the ratio of effective length to least radius of gyration, that is R minimum, and KL effective length we have calculated as 1950, and the R minimum value which is obtained here was 54.1 millimeter. So this was obtained from here only. So here it is this 54.1 millimeter. Now if we take the ratio, we will be obtaining a slenderness value of 36.04. So we round it to be 36, and from table 3 it gives the limit for slenderness ratio, it is less than 180 in page number 20, so it is okay. Now we go to table 8C in page number 38, because our IS HB 350 is in C class. Now we look for the value for this stress reduction factor corresponding to 36. So for 30 it is given as 0.93, and for 40 it is 0.80. So we have to find the value for the, so the yield strength value is 250 only, which is same only. So corresponding to the slenderness ratio of 36, we have to find the value of stress reduction factor. So we have to use the interpolation method. So for 30 slenderness ratio, the value of stress reduction was 0.93. For 40 it was 0.87. So I will be interpolating to find the value of 36. So this will be x, and this will be 0.87. So this based on this interpolation method. So I obtained a value of stress reduction factor for a slenderness ratio 36 as 0.894. Now how can we find the design compressive stress? So this is given in clause 7.1.2.1. It is in page number 34, and its values was psi into Fi divided by gamma m0. Substituting the value of psi as 0.894, Fy as 250 Newton per mm square, and gamma m0 is a design value for the material, and is obtained from table 5. We will be obtaining a design compressive stress of 203.18. So first we study about various methods, and then we will be last multiplying with the effective area. So from this we will obtain the design compressive stress value as 203.18. Now then there is another one quick easy method, and it's a very short method where we can directly calculate the FCD value from the table. So it is given in table 9. So all the table 9A, 9B, 9C, 9D directly give you the design compressive stress value FCD. So our buckling class what we have found was buckling class C. So we have to go to table 9C in page number 42 of our IS 800, and corresponding to our yield stress which is 250 value and the slenderness ratio value which is 36, we have to find the value of the design compressive strength. So for the value for this in 30 was 211, and for 40 it was 198, and we will be using interpolation, and finally we will be getting the design stress as 203.2, and both two methods are found to be having similar values only. Now there is one more method, which is the last method which we can use, and this is basically the equation from the equation which is directly given in our design compressive stress, which was in class 7.1.2. So using that method also we will try to find and getting almost similar values only. So the code has given all these methods. Now in third method, to find the design compressive stress, it's given itself in this clause in page number 34. We can see there is a value called FCC, which is called as Euler's buckling stress. So its equation is pi square E by KL by R the whole square. Basically KL by R is our slenderness ratio, it is 36 only. E is the modulus of velocity, which is 2 into 10 raised to 5. By substituting these values, you will be getting a value of 1523.087. And just about there's a so from this FCC we can calculate the non-dimensional effective slenderness ratio lambda, which is the root of Fy divided by FCC. So Fy is 250 Newton per mm square. FCC is the value which we obtained above. So when I calculate, I obtained a value of 0.405. Now we will be calculating the phi value. The phi value is 0.5 into 1 plus alpha into lambda minus 0.2 plus lambda square. So alpha is the uh, imperfection factor which is given in table 7 and page number 35, and we assume we obtained this particular section has buckling class C, so we'll be taking 0.49. We'll be substituting in our phi equation in which the alpha will be 0.49, lambda is 0.405. We will be obtaining a phi value of 0.632. Now we will be substituting all this into the equation which is giving the design compressive stress, which is given in page number 34, that is Fy divided by gamma m0 the whole divided by phi plus phi square minus lambda square the whole raised to 0.5. Fy is 250, gamma m0 is 1.1, phi is the value which is just calculated 0.632, and lambda is the calculation which is calculated 0.405. And when we substitute that, we have obtained a design compressive stress as 203.43. So all using these three methods, we can basically calculate the FCD value. Now there is also a check for the FCD values, and always this value which we obtained has to be less than or equal to Fy by gamma m0. So that is the factored yield stress, which is 227.27, and this is definitely this 203 is less than 227. Now in the question we have to find the design axial load. Now design axial load is given in clause 7.1.2, which is AE into FCD, where A is the effective sectional area of IS HB 350. And FCD is our design compressive stress, which we just calculated 203.43, and 10 raised to 3 was divided for getting the value in kilonewton. Now AE is the sectional area which is obtained from our IS 808 itself. There is a small a which is sectional area, it was 74.8 centimeter square. So in millimeter square this will be 7480, and multiply will be obtaining the load as 1521.65 kilonewton. So this will be our final answer with our design capacity for the ISHB subject, which is having 3 meter length and having both end fixed.